All right, so what are we looking at here? This is a concave mirror, right? And I drew 5 objects. And so we're going to look and see what type of image is produced from each one of these 5 objects using a concave mirror, okay? And I'll do my best to draw the lines straight. All right, so you can see here, first of all, let's define some of these things. C is the center of this circle. If you were to take this mirror all the way around, right, this would be the center of the circle. And so from C to the surface of the mirror, so this is the normal line to the mirror, right? Normal line always goes perpendicular to the surface. So from here to here is this radius. And you can see that the focal point is 1/2 the radius. Okay, so let's just go ahead and dive in here. You have these 5 objects, okay, and they're going to be producing an image. And you can see, like, here's the red one, here's the blue one, here's the orange one, and over here is the green one, and there is no black one. So first of all, if you have an object that is beyond C, then it will produce a inverted, smaller image. Okay? If you have an object right at the center of the right at the center of this circle, you will produce an image that is the same size but inverted. Now, if you have an object that's in between C and the focal point, it will produce an inverted object that is larger. And then if you have an object at the focal point, you don't produce an image because the lines, which I'll show here in a second, the lines run parallel forever and they don't cross over to make an image. Lastly, if you have an object inside the focal point, in between the focal point and the mirror, you have an image that is produced back here. So it's a virtual, enlarged, upright image. So this is the first example where the image produced is upright. Now, just look at this. Here's the object. All these objects are the same height I made. So as this starts to move in, well, we start here and it's small and inverted. And as we move in, you can see how it grows and this image shifts this way. So as we move in, the objects and the image move in the opposite directions. And it grows. So as this object, right, moves here, the image moves back here and it gets bigger. Okay? And then it grows to infinity as you move it to the focal point. And so the image is not there because this gets so big that it just kind of disappears. It goes to infinity. Then once you pass this point and the object shifts in here, the image isn't formed back here anymore. It starts to become a virtual image. And so as you move from this focal point, start to move in, this image is way back here, right? It's way back here and it's huge. And as you move this way, it starts to come closer and shrink. Okay. So now, looking at a convex mirror, okay? So it's a little bit different. It's always going to be an object produces a smaller virtual object. I mean, a virtual smaller image. So it doesn't matter where you put this, it's going to essentially produce a small virtual upright image. So the magnification is going to be smaller for this one. Over here, you can see that the magnification will be negative because it's inverted, and the magnification will be smaller or less than 1. So because the object, this is the object, and then the image is smaller, so the magnification is smaller. Then the magnification here is just 1, And it's actually -1 because the negative represents an inverted image, and a positive M for magnification would represent a upright image. So this one here would be, magnification would be -1. Now here, magnification is going to be negative, and it's going to be bigger than 1. And then here it's going to be infinity. And then here it's going to be positive, right? It's going to be positive, and it's going to be bigger than 1. And then over here, the magnification will always be positive. I'm sorry. Yeah, it'll always be a positive value, but it'll be smaller than 1 because it gets, magnification is small, right? Okay, so let me come down here and go ahead and start doing this. So let's look at the red object and let's see how the image is formed. So there are 3 lines that you draw. Did I bring my... Oh, shoot. Okay, this will work. Screw it. Grab my little ruler stuff here. Okay, so line 1, we always draw from the top of the object, and it's always going to be parallel. So it hits here. Okay, line 2 always goes to from the top of the object to the center of the mirror. Okay, and then line 3 always goes from the top of the object through the focal point. Okay, bam. Now they're going to reflect, and when these lines cross over, that's where the image will form. So I got to do some measuring, which kind of sucks here. Let's see, 1.5. So right there. So this right here will come through that point. So here's line 1, right? It comes in parallel. Line 2 goes to the center and bounces back with the same angle as it came in, right? There's an angle, there's an angle. Line 3, here, let me label these. Line 3 comes down through the focal point, and then it'll bounce off and be parallel. So it exits parallel with the normal, okay? And then this one right here, it'll bounce at this angle. I can't remember if it bounces through the focal point or not, but it looks like it does. Okay, so that means that this point right here, that will be the image that is produced. Okay. So let's look at this one. What happens? That was beyond C. Now what happens when we are in between C and F, right? So line 1, right? Parallel. Line 2, top of the object to this. And then line 3, top of the object through the focal point. So I gotta get this right. This is pretty tedious stuff here. Bam, and then it exits parallel. So that's always a given. So you can remember this exits parallel. And then you can can't remember if that always goes through the focal point or not. So let's see. It's like three marks. So like right there. So it should come right through here. Okay, and then it does go through the focal point, looks like. Yeah, it's supposed to go through the focal point. Okay, so then this would come down like this. So this does, the line 1 is parallel, and then it always bounces off and goes through the focal point. Line 2, right, bounces from the center and moves this way. Line 3 comes through the focal point and then exits parallel. So that means that the image is, as we saw up in the top example, it's inverted behind it and bigger. And that's the same thing we get here. Okay, so the lines are going this way. All right, so remember where these lines cross over is where the image is being produced. Now let's look at this part. Okay, so here, line 1, let's follow our little rule, parallel. Okay, now it's going to bounce through the focal point. Okay, line 2 goes from here to, from the top of the object to the center. Ooh, that's a little off. About right there. See how tall this thing is? It's kind of a tedious process for it's like less than an inch, or yeah, less than a centimeter. It's like, hold on, what is it? Right there. Okay. Okay, line 2. Hold on, what? Yeah, oh yeah, okay, yeah. Yeah, these lines are diverging, right? So look at this. They're diverging. They're not crossing over, right? This one's going that way. This one's going that way. Now line 3 goes through the focal point, right? So it's going to be like this, right? So here's the thing, we're drawing it towards the mirror. So here's the focal point. We're drawing it towards the mirror. So it would go through the focal point if it was going the other way, but you have to draw the lines going to the mirror, and then it always exits parallel. Remember line 3? So remember line 1 was the enters parallel and exits through the focal point. Line 2 comes down to the center and bounces off. Line 3 goes through the focal point, but since this is in front of the focal point, we have to draw it moving the opposite direction, and line 3 always exits parallel. Now see how these 3 lines are diverging? It won't form an image over here, but what it does do is it produces a virtual image on the, holy crap, did I get this right? Something ain't lining up here. That's gonna, oh, crap. Yeah, this is kind of hard. So here I have to sort of do this. Yeah, okay. I gotta do this. Okay. And then, yeah, I just gotta do this. Okay, so we have to see there's line 2 coming down, bouncing off. So we have to, the lines have to cross over at some point. So here it crosses over on the other side of the mirror and produces a bigger upright virtual image. Okay, so that's going to show you sort of the rules to get these images, right, for each one of these scenarios. Now, looking at this one, it's going to do the same thing, except the lines will cross over right here. Now, for this one, this is at the focal point. So what does that look like? So if we follow the rule, line 1 is parallel and bounces off through the focal point, right? Bam, it's going that way. Line 2 is from the top of the object to the center, and then it bounces off. Let's see, what is that? 1.5 centimeters approximately. Right there. Okay, so it goes that way. Notice that these lines are parallel forever, right? That's a key point. Even this way, they're parallel forever. They will never cross over. Okay, and then line 3 is supposed to go straight through the focal point, right? And you can't even really, Well, we already did this where we bounce it off to go through here, but we can't go straight up and bounce it back through, and we can't go straight down. So there's only two lines that truly exist, because at the focal point, you can't draw the third line. So this was line 1, this was line 2, and they're parallel forever. So there will never be an image formed. So the image forms at infinity is what this is classified as. Okay, so that is the concave examples. Now, looking at the convex example real fast, we got, hopefully I do this right. It's been a while since I'm just following the rules here. Okay, so make sure this parallel, that's the thing. I mean, just the smallest mess up or deviation from like half a degree will screw this up. So, okay, so here we go. Let's see, there's line 1. Here's line 2. Line 2. Let's see where it bounces off. Let's see what, 1 centimeter, almost a little bit over a centimeter. So like right there somewhere. So it'll bounce off that way. Now remember, line 3 goes through the focal point. So here's the focal point. So remember, this is a convex lens. So here's the center of the circle. Focal point is half the distance from here to the center, which is half the radius, right? Okay. Line 3. Line 3 has to go through the focal point. Remember, that's the rule. So like that. Okay, now you can see line 2. Well, here, let's do this. So remember, line 3 always exits parallel to the normal. So it'd be like this. I'll draw it kind of light going that way. Line 1 was right here. So that's line 1. Here's line 2. Here's line 3. Okay, so it would bounce off. Line 3 would bounce off and go parallel. Line 2 would go this way. Line 1 will go, I have to kind of do this because I might have messed it up a little bit, but bounce off that way. So you can see how these 3 lines deviate away and they'll never form an image, but where they do cross is on the opposite side of the convex mirror, and you can see that from these lines we produce a smaller upright virtual image. So the 3 lines cross over back here. Okay, hopefully that made some sense. Now, looking at the formulas. So there are some formulas for the focal point. So here, right, there's some things you need to know. Let's look at this. Okay, so if we're looking at, let's say we're looking at the red. Okay, so from here to here, right, this distance, that's distance of the object from here to here. And then from here to here, this is distance of the image. Okay, so there's a formula. It's 1 over the focal point equals 1 over the distance of the object plus 1 over distance of the image. Okay, now if you remember from the parallel circuit formula, where it was 1 over R equivalent equals 1 over R1 plus 1 over R2. So if there's 2 resistors in parallel, you can use this special formula. So you can do the same thing here. So F equals distance of image times distance of object over distance of image plus distance of object. So there is one formula to remember. Okay, and then also, I've already said this, focal point equals 1/2 the radius. So that's another formula to remember. Okay, now magnification. magnification equals negative distance of image over distance of object. So if the image is bigger than the object, there's going to be a magnification. Okay, and this is also equal to height of the image over height of the object. So you can see here, like in this example, distance of object is a positive value because it's on this side with these points. The distance is on this side. It's not on the opposite side of the mirror, right? So that would be a positive value for distance of object. Then distance of image is also a positive value. So it would be negative. This would be positive and positive. So magnification is going to be a negative value, right? M will equal a negative number. So it's negative because the image is upside down. Okay, and then looking at height. Height of the image is, so here's the set point. This is a negative height and this is a positive height. So height of the image is negative and it's small, and then height of the object is positive and it's bigger, right? So a small number divided by a big number is less than 1. So this magnification would be a negative value, and then it would be a small number. So like negative 0.5 or something, right? Okay, so that is another formula. Okay, and then some key things that I just said. If there is a positive M, that means the image is upright. Negative M is image is inverted. Okay. If this value here, if distance of the image formed is a negative value, so the only time it's a negative value for a concave mirror is when the object is inside of the focal point. You can see that this is a positive distance and this is a negative distance. So whenever there is a negative distance of the image, that is a virtual image. Whenever there's a positive distance of the image, which is over on whenever the image is on this side, right? It's on the same side of the mirror. That is a real image. And what that means is that the image, you can put a screen here, right? You can put a screen in front of the red, or you can put a screen in front of the blue, or you can put a screen in front of the orange, and it will appear on the screen like a piece of paper, right? So light hits these objects, bounces off the mirror, and then will form an image on these screens if you place them there. Now for the green one, there is no way you can put a screen anywhere because the image is behind the mirror. Okay. All right. Okay. Now just to kind of finish up, we're talking about Snell's law and stuff like that. So I'll give you some quick relationships real fast. So here are some mathematical representations. N is a ratio of the speed of light, the speed of light, the maximum speed in the universe, which is light in a vacuum, divided by the speed of light in a medium, right? When there's a medium restricting how fast the light can move. So whenever this reaches a vacuum, C over C is just 1. So when N is 1, that's as small as it gets. Now, this number is always bigger than this number. So N will grow with different materials. So like water, right? Water is 1.33. So that means that this number is bigger than this number because the speed of the light through the water slows down. Okay. And then another one. So you can see it's the max speed over the speed in the medium. Okay, and that means N is also equal to the wavelength of light in a vacuum divided by the wavelength in a medium. Okay, so the wavelength is bigger. The wavelength is bigger in a vacuum, right? The wavelength is longer in a vacuum, and the wavelength actually of light travel or shortens when it goes through a medium. So what that looks like is, let's say that there is this, there's some air and there's water. So what I drew here is, here's the surface of the water. So this is the surface that is between the air and the water. And then this line is called the normal line. So this is the line that you use to make these angles. So let's say that light comes in, red light comes in like this. Okay. And it's a long wavelength. And then let's say it bends. Which way is it going to bend? It's going to bend inwards. It's going to get closer to this line. And the wavelength will be shorter. The wavelength will be shorter. So let me draw this like this, okay, as a straight line, because we don't want all these wavy lines. Okay, so there's a straight line that way, and then it bends, right? Straight line that way. All right, so here is the incoming angle, angle 1, and here is the outgoing angle, angle 2. So out here, n is 1.0, and then in here it's n is 1.33. Okay, so what happens when you go from a small n to a bigger n is the angle gets smaller. So if this is small, the angle is big, and if this is bigger, the angle is small. Okay. All right. So looking at some other formulas here that you need to keep in mind. So there's that. There's that. We got frequency equals speed of light per wavelength, right? And then we can say that's the same thing as speed over wavelength in a vacuum is the same as saying speed in a medium over the wavelength in a medium. Okay, so that's another formula that you'll need to remember. And then lastly, Snell's law. There's a way just to remember all this stuff, and you can rearrange it. Sine of angle 1 divided by sine of angle 2 equals the n2 over n1. Now, then it equals, okay, so 1 and 2 is on top, so the rest of them are just 1's on top. So velocity 1 over velocity 2 equals, so this also equals wavelength 1 over wavelength 2. So you can set these two equal to each other, or you can set these two equal to each other, or whatever you want to do. Now, one more thing you need to know for this chapter is Vn, right? Multiply both sides by Vn and then divide both sides by n. To just rearrange this formula, you got Vn, bring it over here, and then bring n down here. C over n. Okay? Now, what is velocity equal to? It's also equal to distance over time. So then you can also set these two equations equal to each other, right, to solve for time. So there's a problem where that is that's involved. Okay, lastly, now I'm showing another example here. Here's water, right? Water, and here is oil. Okay, so in here is 1.33 and in here is 1.48. Okay, so let's say we have a incoming ray with this angle, angle 1. So remember, the angle is always between the normal line that runs perpendicular to the surface between the two mediums. Now, which way will this angle exit? Will it be like this, where the angle is smaller, or will it be like this, where the angle is larger, right? So remember, if this is smaller than this, if this is small, this one's big. Since this one's bigger than this, the angle will be smaller. So there's a inverse relationship there. Now remember, the angle is always between the ray and the normal vector. So that would be angle 2. So it would be coming in and the angle decreases. Now let's draw another example over here. Let's say that the ray is coming, here I'm gonna make it kind of sharp. It's coming through the oil this way, right? So here's the angle. There's angle, well, that's angle 2. Which way would this exit? Is it going to be like this? Or is it going to be like this? Right? So just think about that for a second. So it's hitting right here. I got the normal line this way. So it's actually going to be steeper. Right? It'll be steeper. Because here's the angle. Remember, the angle is always between the ray and the normal vector. Because bigger number, smaller angle. Smaller number, bigger angle, right? Now, there's also this concept where if you get this, let's make one more normal. If you get this sharp enough, this angle sharp enough, right? Incoming ray, remember it's always between the ray and the normal. Well, there's a point where this becomes, right? The exiting ray runs 90 degrees. 90 degrees. Okay, so this would be called the critical angle. So using our formula over here, so sine of theta 1 over sine of theta 2 equals n2 over n1. Now sine of theta 2, this is theta 2 right here, right? 90 degrees. What's sine of 90 degrees? That's just 1. So this is sine of theta 1 equals n2 over n1. Now this is called the critical angle. Whenever this becomes 90 degrees, sine of 90 degrees is just 1, and then you have this. Okay, so this would be called the critical angle when the incoming ray is sharp enough to where the exiting ray runs parallel to the surface, which is the same as saying runs 90 degrees to the normal. Okay, and then if you're solving for critical angle, it would be critical angle equals the inverse sine of n2 over n1.